Good morning, class. Today we're going to go over briefly what we learned yesterday on our lesson based on latitude with consideration of the altitude of Polaris. So let's grab your notes, and we're going to do a brief overview before we have a quiz on this later this week. Okay. Here we just have a picture, a really neat picture actually that I found from one of our textbooks, just showing a little description of the stars in the atmosphere and the beautiful landscapes in the background. Now, I hope you remember from class that the latitude equals the altitude of Polaris. That's very important to remember. Polaris can only also be seen in the northern hemisphere. So in the United States, we definitely have a visible view of Polaris. Polaris is also called the North Star. So in case some of your books mention the North Star or Polaris, they're both meaning the same thing, but you can only see it in the northern hemisphere. So if our latitude is 25 degrees north and our longitude is 100 degrees west, the altitude of Polaris would be 25 degrees. Okay, so we are in the northern hemisphere, so we do have the Polaris North Star visible, and it's the same altitude as our latitude, which is 25 degrees. Now, if our location is 30 degrees south and 100 degrees east, we cannot see Polaris because Polaris is not visible in the southern hemisphere. Very important to remember. Also, if we're at 80 degrees south and 65 degrees west, we're still in the southern hemisphere, so Polaris cannot be seen. Next, if we're at 45 degrees north and 105 degrees east, Polaris will be visible at an altitude of 45 degrees. Now, it does not matter whether we're in the eastern hemisphere or in the western hemisphere. We're only concerned about our latitude and whether or not we're in the southern or northern hemisphere. Okay, longitude is based on the Earth's rotation, and that is dependent on many factors, as we're going to go over again. Longitude is based on the Earth's rotation, and each hour the Earth rotates 15 degrees. So the Earth is approximately 360 degrees, and within 24 hours it makes one complete rotation. So if you divide that by hour, we rotate 15 degrees per hour. Okay, looking at a flat version of the globe, how many time zones do we have? Now take a minute to think about this. If we have 1 hour equals a 15-degree span, divide that by 360, and how many time zones do we get? We have 24 time zones that are 15 degrees apart. Okay. People on the same line of longitude have the same local time. That's very important to remember. If you think about the United States, we have different time zones. Here in New York, we're in the Eastern time zone. But as you move further on to the west, as you go 15 degrees more, they get an hour behind us. So in the central time zone, consisting of Chicago, a little bit of the Midwest, along the Mississippi River, those guys are approximately 1 hour behind us. Then you have Mountain Time, then you have Pacific Time, and as you keep going further west, they get an hour behind us. So in California, they are at Pacific Time, which is approximately 3 hours behind us. So if it's 6 o'clock p.m. right now, it is only 3 o'clock p.m. in California. Okay, and last we're going to do an example. If two students record a difference in local time of 2 hours, how many degrees of longitude are they apart? Okay, so if they have a difference of 2 hours, we're looking for the amount of degrees. So 2 hours times 15 degrees equals 30 degrees. So that would be a good review problem for an upcoming quiz. So I'd make sure we study this if you didn't already know the correct answer. So that's our brief review of latitude and longitude and how it affects Polaris and the time zones. So let's review your notes one more time, and then we're going to work on a different work plan and have a quiz on this early next week.